Long before the first astronomer pressed an eye to a polished lens, long before ancient priests carved the earliest sky charts into soft clay or painted them onto the inside walls of forgotten tombs, humanity felt the silent pull of wandering lights drifting across the night. They drifted with purpose, unlike the fixed stars, moving night after night against the distant tapestry, drawing attentive minds toward patterns woven not by chance, but by a cosmic machinery, both intimate and unreachable. In this slow dance of distant fires, people sensed stories, omens, seasons, and rhythms older than language itself. From the banks of the Nile to the plains of Mesopotamia, from the stone observatories of Mesoamerica to the wind-swept steppes of Central Asia, civilizations intimately tied their fates to these drifting points. Yet the deeper truth of their nature, the immense worlds orbiting our shared star, remained invisible, wrapped in myth and metaphor, until time and curiosity forced the heavens to give up their secrets, piece by piece. The ancient Babylonians, meticulous sky recorders of the first order, tracked the so-called wandering stars with obsessive precision, filling tablets with ephemerides that today survive baked into brittle cuneiform. They noted how one moved swiftly near the dawn, another glowed with a strange golden steadiness, another reddened like an ember smoldering at the horizon. Their predictions of planetary motion were acts of devotion and power, harnessed to the belief that each celestial wanderer embodied a deity whose moods shaped the destiny of kings. Even though their interpretations were couched in religious symbolism, their mathematical models for planetary motion formed some of the earliest frameworks of astronomy, refined further by the Greeks who inherited their records. To the Greeks, these planets were gods strolling across Olympus with leisurely dignity. Mercury was Hermes, fleet-footed and elusive. Venus became Aphrodite, the luminous jewel of the morning. Mars blazed as Ares, temperamental and red-blooded. Jupiter, brightest of them all, embodied Zeus, lord of the sky, while Saturn became Cronus, ancient and grim. Yet even as their mythology colored each planet's personality, philosophers like Pythagoras, then Eudoxus, and finally Ptolemy built layered geometric models to explain the subtle arcs and loops these wandering stars traced against the constellations. Their epicycles, those circles upon circles, were an elegant, if ultimately flawed, attempt to reconcile observation with an Earth-centered universe. For centuries, the planets remained both familiar and inscrutable, until the quiet revolution of the Renaissance ripped open the sky. When Nicholas Copernicus wrote De Revolutionibus Orbium Celestium, he shifted the universe from a stage with Earth at its center to one where the sun commanded the choreography. The planets, once thought to revolve around us, instead circled the sun in grand, sweeping paths. At first, his model was as controversial as it was transformative, for it challenged not only celestial.
Then came Galileo Galilei, turning his crude telescope toward the heavens and stumbling into a minefield of contradictions that threatened the old worldview. He saw Venus waxing and waning, like our moon, a phenomenon impossible under a geocentric model, but perfectly natural in a sun-centered system. He found 4 moons circling Jupiter, worlds orbiting a world, demonstrating that Earth's monopoly on satellites was an illusion. The planets began to show their faces to us, no longer abstract points of light, but disks, worlds, and spheres with distinct characters. The cosmos expanded from symbolism into substance. From here, the story of the planets becomes not just a journey of human discovery, but a continuous unraveling of the layers that built our solar neighborhood. Each planet, Mercury, scorched and battered, Venus, shrouded and simmering, Earth, fertile and restless, Mars, cold and whispering of ancient water. Each holds its own chronicle, etched into rock, atmosphere, and orbit. Jupiter, swollen with storms older than civilizations. Saturn, veiled in rings whose glitter belie violent origins. Uranus, tipped askew like a celestial oddity. Neptune, deep blue and storm-lashed beneath its methane skies. Each is a chapter in an epic that spans billions of years. But to understand them historically, as though watching an immense chronicle play out over cosmic epochs, we must journey back to the era when none of these worlds yet existed. When the sun itself was a newborn star, surrounded by a swirling, luminous disk of dust and ice. In this turbulent cradle, planetary formation unfolded like a slow explosion, sculpted not by fire, but by gravity. Dust grains collided and clumped, forming pebbles, then boulders, then mountain-sized planetesimals. Through relentless impacts and gravitational competition, these early fragments grew, devoured rivals, and carved out orbital lanes in the protoplanetary disk. The inner zone, hot and volatile, forged rocky, metal-rich worlds, while the outer coldness allowed gases and ices to accumulate into enormous giants. Each planet was shaped not only by its materials, but by its distance from the forming sun, its encounters with siblings, and its own violent internal transformations. Mercury, the smallest and densest of the terrestrial planets, likely began much larger before suffering catastrophic collisions that stripped away much of its mantle, leaving a world dominated by an oversized iron core. Its surface became a mosaic of scars, vast basins like Calorus, formed by early impacts whose shock waves rippled through the entire planet, creating wrinkled ridges on the opposite side, as though Mercury itself resonated like a gong struck by a celestial hammer. Its proximity to the sun locked its rotation into a peculiar resonance. 3 spins for every 2 orbits, a rhythm governed by tidal forces that tug endlessly at its metal heart. Venus, by contrast, began as Earth's twin, similar in size and composition, but diverged catastrophically. Where Earth cooled enough for oceans to gather and moderate its climate, Venus endured a runaway greenhouse effect. Early water vapor, unable to condense,
Earth, occupying the narrow band of temperate sunlight that allows liquid water to persist, became something astonishing. Its early bombardment delivered essential volatiles, and its restless tectonic plates recycled carbon, regulated climate, and sculpted continents. Life emerged, transforming the atmosphere with oxygen long before complex organisms arose. Our planet's narrative intertwines geology, chemistry, and biology in ways that no other planet yet observed can match, though Mars once came closer than we ever imagined. Mars, the red relic of a once warmer world, reveals evidence of river valleys, deltas, and lakes that persisted for millions of years. Its faint magnetism marks the ghost of a vanished global magnetic field, whose disappearance allowed solar winds to strip away atmosphere and evaporate the surface water into the void. Ancient sediments preserve minerals formed in neutral or mildly alkaline waters, conditions under which primitive life might have thrived had it ever arisen. Volcanoes like Olympus Mons tower over the planet, their immense heights possible because Mars's lower gravity allowed eruptions to build structures impossible on Earth. Beyond the asteroid belt, the solar system's titanic rulers dominate. Jupiter, immense enough to be nearly a failed star, radiates more heat than it receives, a remnant of the gravitational contraction that once fueled its growth. Its great red spot, a storm large enough to swallow Earth, has raged for centuries, though modern measurements reveal its slow shrinkage over time, as though reminding us that even ancient tempests have lifespans. Jupiter's magnetic field, the strongest of any planet, traps deadly radiation that shapes the environments of its many moons. Moons that themselves form miniature planetary systems, like Europa with its hidden subsurface ocean, or Io with its savage volcanic eruptions driven by tidal stress. Saturn, though less massive, captivates with the grandeur of its rings, icy shards formed perhaps from a shattered moon or an undifferentiated cometary body torn apart by tidal forces inside the Roche limit. These rings, dynamic and structured, ripple with waves created by moonlets that shepherd their edges. Saturn's atmosphere hosts hexagonal polar storms whose geometry defies intuition, while its moon Titan harbors lakes of liquid methane and ethane, cycling through weather systems analogous to Earth's but operating at temperatures hundreds of degrees colder. Uranus, that pale, distant enigma, rotates nearly on its side, likely tipped by a primordial collision that reoriented its axis and altered its internal heat distribution. Its faint rings and icy moons orbit in this strange sideways configuration, as though the entire system were a cosmic sculpture tilted against expectation. Neptune, farther still, churns with winds faster than any in the solar system, whipping its methane clouds into fleeting storms that appear and vanish with surprising speed. Its moon Triton, likely a captured Kuiper belt object, orbits backward relative to Neptune's rotation, slowly spiraling inward as tidal forces tug it toward an eventual destruction that may produce new rings centuries from now.
Yet the planet's stories did not end with their formation. Their histories continued through billions of years of bombardment, migration, orbital resonances, and internal evolution. Even today, subtle changes unfold. Mercury's orbit precesses due to relativistic effects. Venus rotates sluggishly under atmospheric tides. Earth's climate cycles through glacial epochs. Mars continues to lose atmosphere. Jupiter's storms morph and migrate. Saturn's rings slowly erode. Uranus and Neptune shift in brightness as seasons, lasting decades, transform their cloud patterns. To narrate the epic of the planets is to trace an ongoing saga where ancient events echo through present-day features, and present dynamics hint at future transformations. Across the vast gulf of time, these transformations accumulated like layers of sediment in a planetary archive, each stratum preserving clues for future minds determined to decipher them. As human civilizations advanced, so too did their means of probing the heavens. The medieval Islamic world, inheriting Greek texts and expanding them with innovative mathematical techniques, refined planetary tables, and established observatories that became intellectual beacons from Samarkand to Cordoba. Astronomers such as al-Battani and Ibn Yunus achieved measurements of planetary motions whose precision would astonish their European successors centuries later. Their instruments, armillary spheres, astrolabes, and mural quadrants allowed systematic observations that chained the knowledge of past cultures to the discoveries of new eras. But it was the invention of the telescope that truly opened the gateway. After Galileo's revelatory observations, a cascade of discoveries followed. Christian Huygens resolved the true nature of Saturn's rings, realizing they were not strange appendages, but a broad, flat system encircling the planet. He also discovered Titan, Saturn's largest moon, whose subdued orange glow hinted at mysteries beneath thick atmospheric veils. Giovanni Cassini later identified divisions within Saturn's rings and uncovered additional moons, each discovery peeling away the planetary mystique one layer at a time. Meanwhile, careful observation of Mars's seasonal changes led Christian Huygens to map its southern polar cap in 1659, the first clear indication that Mars possessed features governed by climatic cycles not entirely unlike Earth's. As telescopes grew larger, their resolving power improved, revealing the planets as places with texture, patterns, and shifting phenomena. The 19th century marked an era of frenetic astronomical discovery.
In 1781, Sir William Herschel, sweeping the sky with his meticulously crafted telescopes, stumbled upon Uranus, the first planet found in recorded history rather than inherited from ancient knowledge. Its discovery shattered the notion that the solar system ended at Saturn and hinted that the cosmos still held surprises beyond the reach of naked eyes. Uranus's slow orbit and faint appearance invited patient study, and as astronomers refined its trajectory, they noticed puzzling irregularities. These deviations suggested the gravitational tug of another unseen body farther out, prompting an international race to calculate its possible position.
In 1846, guided by the mathematical predictions of Urbain Le Verrier and John Couch Adams, Johann Galle identified Neptune within a degree of its forecasted location. The success stunned the scientific world, demonstrating that mathematics could reveal a planet without ever seeing it. It was as though the solar system itself had whispered its secrets through the language of gravity. Neptune's discovery cemented celestial mechanics as a cornerstone of astronomy and encouraged the search for additional bodies that might similarly reveal themselves through subtleties in orbital motion. The 20th century ushered in a technological revolution that transformed planetary exploration from a distant dream into a tangible reality. Spectroscopy dissected planetary atmospheres, revealing their compositions by analyzing the distinct fingerprints of light absorbed or emitted. Radio astronomy pierced cloud layers, penetrating the opaque shroud of Venus to reveal its scorching surface conditions. Infrared observations measured temperatures and traced heat signatures, while photographic plates captured details invisible to earlier generations. But it was the advent of rocketry, born from military conflict and repurposed in peacetime, that finally allowed humanity to send instruments beyond Earth's grasp. In 1962, NASA's Mariner 2 spacecraft became the first successful planetary probe, flying past Venus and confirming its furnace-like environment. This discovery overturned earlier romantic speculation that Venus might host jungles or oceans hidden beneath its clouds. Instead, its surface baked at temperatures hot enough to melt lead, under pressures akin to being submerged hundreds of meters underwater on Earth. The revelation forced scientists to re-evaluate assumptions about planetary climate and the delicate balance that made Earth habitable. 2 years later, Mariner 4 captured humanity's first close-up images of Mars. The photographs revealed a cratered desert world, dry and seemingly lifeless, far removed from the canal-filled fantasies that had captivated the late 19th century. Yet this bleak portrait was only a fragment of Mars's true history, a surface snapshot of a planet whose ancient past remained buried beneath dust and stone. Subsequent missions, Mariner 9, Viking, Pathfinder, and beyond, would unveil dried riverbeds, sedimentary layers, and minerals formed in aqueous environments.
painting a far more complex narrative. The exploration of the outer planets began in earnest with the Voyager missions of the late 1970s. Launched in 1977, Voyager 1 and Voyager 2 embarked on a grand tour made possible by a once-in-76-year alignment of the outer planets. Using gravity assists, they leapt from one planetary giant to the next, carrying cameras and instruments that provided humanity with unprecedented glimpses of alien worlds. When Voyager 1 approached Jupiter in 1979, its images exposed a storm-racked world far more dynamic than Earth-bound telescopes had ever revealed. Volcanic eruptions on Io, bluish plumes arcing into space, electrified.
These revelations fundamentally altered our understanding of planetary systems. No longer could planets be viewed as static, isolated entities. They were dynamic environments, interacting with their satellites, rings, magnetic fields, and the solar wind. The diversity of conditions within a single planetary system suggested that variety on a cosmic scale might be far greater than imagined. While robotic probes ventured outward, Earth-based studies continued to unearth secrets about planetary evolution. Isotope analysis of meteorites provided clues to the early solar system, preserving the composition of primordial material. Ice cores and geological strata on Earth revealed the interplay between our planet's orbital variations, Milankovitch cycles, and long-term climate patterns. These cyclical changes in Earth's orientation and orbit underscored the gravitational relationships among planets and highlighted how subtle interactions across millions of years dramatically shaped global environments. Within this grand celestial architecture, planetary migration, once dismissed as unlikely, emerged as a crucial factor in the solar system's formation. Computer simulations suggested that Jupiter and Saturn, during their early evolution, shifted positions, disturbing the orbits of smaller bodies and sculpting the asteroid belt into its present form. Uranus and Neptune may have traded places as gravitational interactions with the surrounding disk of icy planetesimals propelled them outward. These migrations redefined our understanding of how gas giants influence terrestrial planet formation and provided insights into the architecture of exoplanetary systems scattered throughout the galaxy. As telescopic technology advanced, refinements in adaptive optics, mirror segmentation, and space-based observatories allowed astronomers to observe the planets with extraordinary clarity. The Hubble Space Telescope captured storms on Neptune, seasonal haze on Uranus, auroras flickering on Jupiter's poles, and volcanic plumes on Io erupting above its sulfurous plains. Meanwhile, orbiters like Cassini became long-term residents of distant worlds, chronicling Saturn's seasons, Titan's shifting hydrocarbon lakes, and the restless geysers of Enceladus that sprayed water vapor into space from a subsurface ocean warmed by tidal forces. These missions enabled scientists to trace interactions across scales, from microscopic organic molecules on Titan's dunes to planetary-scale circulation patterns shaping Venus's super-rotating winds. Venus, once thought to be a static inferno, revealed an atmospheric dynamism that included gravity waves rippling across its cloud tops, vortices twisting above its poles, and a puzzling discrepancy between the slow rotation of the planet and the rapid motion of its upper atmosphere. Mars, revisited by a fleet of orbiters, landers, and rovers, slowly yielded its buried narrative. The Spirit and Opportunity rovers discovered hematite spherules, blueberries, formed in ancient water. Curiosity traced complex organic molecules in Martian rocks, and the Mars Reconnaissance Orbiter imaged recurring slow. The story of the planets, however, is not confined to the realms of large, familiar worlds. The asteroid belt, long perceived as a chaotic rubble field, became a critical chapter in this narrative. Asteroids like Vesta and Ceres preserve records of early planetary differentiation and hydration. Ceres, with its bright salt deposits and suspected briny subsurface reservoirs, expands the possible niches for life within the solar system. Farther out, the Kuiper Belt hosts icy relics whose orbits preserve the memory of early migratory upheavals. Pluto, once considered the ninth planet, revealed through the New Horizons mission a surprisingly active world with nitrogen glaciers, cryovolcanoes, and an atmosphere that expands and collapses with its elongated orbit. And still farther, in the vast expanse of the Oort cloud, trillions of icy bodies drift in a distant halo, remnants of the solar system's earliest days, perturbed occasionally by passing stars or galactic tides, sending long-period comets plunging inward like time capsules from the cosmic frontier. These ephemeral visitors, burning into incandescent streaks near the sun, carry with them the chemistry of primordial materials, offering insights into the ingredients present when the planets were newborn. Even today, as astronomers search for patterns in the long-term stability of the solar system, simulations reveal a delicate balancing act spanning billions of years. The gravitational interplay among planets create regions of chaos and resonance, shaping the trajectories of smaller bodies and occasionally destabilizing orbits over eons. Jupiter, acting as both shield and shepherd, deflects or captures comets that might otherwise threaten Earth, yet occasionally sends others inward toward the inner planets. Saturn's resonances influence asteroid belt dynamics, while the combined gravitational fields of Uranus and Neptune structure the Kuiper Belt's orbital families. The solar system remains a living, evolving structure whose behavior unfolds across timescales far beyond human lifespans. The deeper scientists looked into these harmonies and disruptions, the more they recognized that the planets were not isolated actors, but participants in a vast gravitational symphony whose notes resonated across epochs. Subtle shifts in orbital eccentricities, inclinations, and axial tilts gradually altered patterns of sunlight and climate. On Earth, these celestial modulations helped guide the pacing of ice ages, the advance and retreat of glaciers, sculpting continents like a patient artist reshaping an ancient canvas. On Mars, the absence of a large moon of any significant size, and locked in its slow retrograde rotation, developed atmospheric superrotation driven by complex interactions between solar heating, planetary rotation, and turbulence within its dense cloud layers. Its atmosphere, a colossal engine circling the planet in just 4 Earth days, draped Venus in perpetual tempest. Yet these winds obeyed physics.
Meanwhile, the study of Jupiter revealed that even a gas giant's internal composition and weather systems encoded the memory of its formation. The Galileo probe, which descended into Jupiter in 1995, sent back measurements of pressure, temperature, and chemical abundances before being crushed by the immense weight of the atmosphere. Its findings, combined with decades of observations, suggested that Jupiter's core might be diffuse, its boundaries blurred by immense pressures that dissolve traditional distinctions between solid, liquid, and gas. Layers of metallic hydrogen deep within Jupiter generate Jupiter's powerful magnetic field, a force so vast that it carves a cavity in the solar wind and funnels charged particles into spectacular auroras at the poles. Auroras far larger and more energetic than Earth's most vibrant displays. Saturn offered its own revelations. Beneath the beauty of its rings lies a history marked by destruction and renewal. As Cassini orbited the planet for more than a decade, it observed wave patterns rippling through the rings caused by the gravitational influence of Saturn's moons. Each ripple, each gap, each shepherded edge represented a dynamic relationship between fragments of ice and orbiting satellites, a ballet of interactions so subtle that the entire system could be considered a record of Saturn's past. Rings brightened or dimmed with sunlight, accumulated or shed dust, and shifted ever so slightly in response to meteorite bombardment. Even the hexagon at Saturn's North Pole, an astonishing geometric cloud formation discovered by Voyager and studied extensively by Cassini, revealed the complexity of atmospheric circulation, a planetary-scale standing wave unlike anything seen elsewhere in the solar system. Uranus and Neptune, long distant and enigmatic, yielded their secrets more slowly, with only brief visits from Voyager 2 and careful follow-up observations from Earth and space telescopes.
Uranus's sideways spin puzzled scientists for decades, leading to theories of a colossal collision early in the solar system's history. Such an impact could have disrupted its internal heat distribution, leaving the planet radiating far less energy than expected and rendering its atmosphere relatively featureless in visible wavelengths. Yet under infrared scrutiny, faint storms and cloud systems appeared, shifting slowly across its pale surface like ghostly fingerprints of atmospheric motion. Neptune, more active and internally warm, displayed rapidly evolving storms that sprang into existence, shifted latitude, and vanished within mere years, defying the earlier assumption that the outer planets' atmospheres were sluggish and inert. As the 20th century gave way to the 21st, planetary science embraced new paradigms driven by expanding technologies. The search for exoplanets, planets orbiting other stars, revealed systems wildly different from our own. Hot Jupiters, super-Earths, many Neptunes, and worlds orbiting perilously close to their parent stars challenged assumptions built on the architecture of our solar system.
With each discovery, the stories of our solar system and the wider galaxy became intertwined. Observations of exoplanetary atmospheres illuminated processes that likely occurred on early Venus or Mars. Studies of disks around young stars revealed stages of accretion and migration similar to those that shaped Jupiter and Saturn. Comets originating from the cold reaches of the Kuiper Belt and Oort cloud were compared to icy bodies around distant suns, revealing the universality of certain cosmic ingredients, water, carbon, silicates, distributed throughout the galaxy like seeds awaiting the right conditions for new worlds to emerge. Meanwhile, robotic explorers continued their meticulous work across our planetary neighbors, carving new chapters into the narrative. On Mars, the InSight lander recorded Marsquakes, mapping the planet's internal structure and confirming the existence of a liquid outer core. Perseverance rolled across Jezero crater, a site once filled by a long-vanished lake, analyzing sediments that had settled in tranquil waters billions of years ago. The rover's microphones captured the whispering breeze of another world, a sound that carried across the Martian landscape like the faint echo of an ancient climate. Ingenuity, the small helicopter accompanying Perseverance, achieved powered flight in the thin Martian atmosphere, an accomplishment that, though brief in duration, represented a leap in technological confidence for exploring worlds with challenging environmental conditions. Elsewhere, probes like Juno transformed our perspective on Jupiter, flying through its polar regions and mapping its deep atmospheric currents. Juno revealed that the Great Red Spot extended far deeper than predicted, a towering formation rooted deep in Jupiter's turbulent layers.
Its gravity measurements provided insights into the planet's internal distribution of mass, challenging previous models that envisioned a sharply defined core. The swirling cyclones around Jupiter's poles, arranged in stable geometric patterns, prompted questions about the interplay of rotation, convection, and planetary magnetism in the formation of such enduring structures. Saturn's moon Enceladus, with its geysers venting water vapor, organic molecules, and microscopic ice grains into space, became a prime candidate in the search for extraterrestrial life. Cassini flew through these plumes repeatedly, sampling their composition and identifying complex organic compounds that hinted at hydrothermal processes beneath the moon's icy crust. If life could arise in such a dark, enclosed ocean, warmed not by sunlight, but by tidal heating, then potentially millions of similar icy worlds scattered throughout the galaxy might harbor biology in forms we have yet to imagine. Titan, larger than the planet Mercury, captivated scientists with its methane cycle, a counterpart to Earth's hydrological cycle. Rivers of liquid. Even Mercury, long considered geologically inactive, surprised researchers with evidence of recent tectonic activity. Its surface scarps, cliffs formed by planetary contraction, appeared younger than expected, suggesting that Mercury continued to cool and shrink long after scientists believed such processes should have ceased. Messenger, the first spacecraft to orbit Mercury, mapped its surface in unprecedented detail, revealing hollows, bright, irregular depressions formed by volatile loss, whose existence challenged assumptions about Mercury's composition and thermal history. All these discoveries, integrated across missions, laboratories, and observatories, coalesced into a tapestry of planetary science far richer than the simplistic models of earlier centuries. Each planet's story expanded beyond its physical description into a chronicle of environmental transformation, interior evolution, orbital dynamics, and chemical complexity. From the scorched rocks of Mercury to the icy plains of Pluto, the solar system emerged as a system shaped by both universal laws and local accidents, an interplay that produced the worlds we know today. In parallel, Earth-based laboratories recreated planetary conditions through sophisticated simulations. Shock compression experiments mimicked the pressures inside gas giants, while vacuum chambers simulated the frigid, thin atmospheres of outer moons. Geochemists analyzed isotopic ratios in meteorites, tracing them back to regions of the protoplanetary disk and revealing that even small variations in temperature and composition had enormous consequences for planetary development. Computer models mapped early solar system dynamics, showing how gravitational interactions could sculpt planetary systems into vastly different architectures depending on initial conditions. These models offered retrospective glimpses into the chaotic infancy of the solar system, when planets competed for space and resources in a cosmic arena defined by collision, accretion, and migration. As planetary science entered this modern era, the line between historical narrative and scientific inquiry blurred. Each crater, every dune, every spectral signature became a clue to past events, reconstructing a history spanning billions of years. The solar system became not merely a collection of worlds, but a chronicle of processes: accretion, differentiation, volcanism, tectonics, erosion, climate cycling, atmospheric escape, magnetospheric. As these questions multiplied, so did the instruments crafted to pursue them. The James Webb Telescope, operating far from the interference of Earth's atmosphere, began observing planets and moons in infrared wavelengths that revealed heat signatures, molecular compositions, and atmospheric structures with unparalleled sensitivity. Its detectors pierced through Jupiter's haze layers, exposed the thermal glow of volcanic eruptions on Io, and traced the faint cold signatures of methane clouds drifting across Uranus and Neptune. Each observation refined models of planetary weather, chemistry, and internal heat flow, deepening the understanding of how even distant, frigid giants remain dynamic in ways hidden from earlier generations of astronomers. Meanwhile, ground-based observatories equipped with adaptive optics transformed Earth's mountains into rival vantage points. By counteracting atmospheric distortion with real-time adjustments to mirror shape, these telescopes snapped images of planetary surface features that once required spacecraft flybys. Dust storms blooming across Mars, storms churning on Neptune, faint spokes forming within Saturn's rings, all became observable with clarity unimaginable to the astronomers of the 20th century. Together, space and ground-based observations created a multi-layered portrait of the planets, capturing them simultaneously across wavelengths, timescales, and vantage points, revealing how their atmospheres evolved day by day, season by season. Beyond observation, there was experimentation. Laboratories meticulously recreated the chemistry of early Earth and Titan, simulating lightning strikes in methane-rich atmospheres and analyzing the resulting compounds. These experiments produced tholins, complex organic molecules believed to exist on Titan, whose reddish-brown hues and sticky textures suggested how prebiotic chemistry might have flourished on worlds far from warmth. In facilities chilled to cryogenic temperatures, researchers compressed ices under pressures replicating the interiors of icy moons, examining the transition of water into exotic phases like Ice 2, Ice 5, and Ice 6. These unfamiliar forms, stable only at extreme conditions, hinted at the layered structures inside moons such as Ganymede and Callisto, where internal oceans might reside between strata of high-pressure ice. Planetary magnetism, too, became a frontier of inquiry. Earth's magnetic field, generated by convection within its molten outer core, shields life from harmful radiation and guides migratory animals across continents. But other planets offered contrasting examples. Mercury, though small, harbored a surprisingly strong magnetic field, suggesting partial core fluidity despite its size. Venus lacked an intrinsic magnetic field entirely, its slow rotation unable to sustain the dynamo process, exposing its atmosphere to relentless stripping by the solar wind. Mars preserved only remnant magnetism frozen into its crust, relics of an ancient field long extinguished. Jupiter's magnetosphere dwarfed all others, its magnetosphere extending beyond the orbit of Saturn at times, influencing charged particles and radiation belts on scales unimaginable on Earth. Studying these magnetospheres illuminated the relationships between planetary interiors, rotation rates, and as the scope of planetary exploration broadened, so too did the ambitions of mission planners. Proposals for sample return missions multiplied, each designed to retrieve pristine material from places where history lay most clearly written. Samples from Mars could answer questions about the planet's habitability, while material from the moons of Mars, Phobos and Deimos, might preserve fragments of early Martian crust thrown into space by ancient impacts. Missions targeting Ceres, Jupiter's moons, cometary nuclei, and Kuiper Belt objects promised to deliver diverse samples that would transform planetary science from remote sensing into direct laboratory analysis. At the same time, engineers turned their attention to new modes of exploration. Submersible probes designed for the icy oceans of Europa and Enceladus were studied, capable of melting through kilometers of ice to reach dark seas warmed by tidal energy. Aerobot balloons envisioned drifting within the thick atmosphere of Venus, riding high above the searing surface where temperatures moderated enough to support long-duration operations. Flying drones were proposed for Titan, their rotors slicing through the dense air with ease, landing near lakes of methane to analyze surface materials and atmospheric chemistry. Each new design recognized that the diversity of planetary environments demanded tools as varied as the worlds themselves. Yet even as future missions were imagined, the historical narrative of planetary exploration remained rooted in the ancient instincts that first drew human eyes to the night sky. The planets had always blended mystery and familiarity, anchoring cultural stories from the earliest civilizations. The Maya aligned temples to track Venus, believing its cycles influenced fate and warfare. The Chinese maintained records of planetary motions that spanned millennia, incorporating them into astrology and imperial decision-making. Greek philosophers sought the underlying geometry behind planetary paths, while Islamic scholars refined models and preserved knowledge through centuries of intellectual upheaval. The Renaissance reawakened curiosity after long dormancy, and the scientific revolution transformed that curiosity into systematic inquiry, launching humanity onto a trajectory that led from myths scratched into clay to spacecraft sailing between worlds. The modern era of exploration, though powered by advanced mathematics, elaborate instrumentation, and global cooperation, remained part of this lineage. Spacecraft names echoed historical figures: Galileo, Cassini, Huygens, reminding each generation of explorers that their achievements rested on a foundation laid by those who first dared to question the static perfection of the heavens. Each discovery, whether a new storm on Jupiter or organic chemistry on Titan, expanded not only scientific understanding, but the human sense of place within the cosmos. Observations from Mars revealed a planet whose ancient rivers and deltas recorded a once warmer, wetter climate, broadening perceptions of where life might arise. Images of Europa's cracked ice and Enceladus, its geysers, redefined the boundaries of habitability, suggesting that oceans warmed by tidal forces could shelter life in environments independent of sunlight. Titan's methane lakes raised the possibility of exotic chemistries fueling life unlike anything on Earth. Even Venus, long dismissed as a hellscape, renewed interest with studies proposing that its temperate past might have supported oceans before runaway greenhouse warming transformed it. These revelations forced scientists to reconsider what a habitable world looked like, not merely a terrestrial planet in a temperate orbit, but any environment where energy, chemistry, and liquid solvents intersected. Subsequent modeling of planetary atmospheres included not only greenhouse gases and thermal profiles, but also photochemistry driven by stellar radiation, the influence of magnetic fields, and the role of volcanic outgassing. Researchers simulated how early Mars might have cycled water through volcanic release, atmospheric escape, and regolith absorption. They studied how early Earth's atmosphere shifted from methane-rich haze to oxygenated clarity, tracking the influence of microbial life on planetary climate. They examined why Venus diverged into a runaway greenhouse while Earth stabilized, focusing on feedback loops involving clouds, surface composition, and solar luminosity. These comparative planetologies allowed Earth's history to be viewed not as an isolated account, but as one instance within a larger array of planetary fates. While robotic missions and telescopic observations pushed the boundaries of scientific knowledge, the theoretical exploration of future planetary evolution unfolded in parallel. Simulations projected how the sun's gradual brightening would transform the inner planets over the next billion years. Mercury, already scorched, would continue to heat until its surface resembled molten terrain. Venus's already unbearable temperatures would rise further, possibly altering its atmospheric dynamics in unpredictable ways. Earth, despite its stabilizing mechanisms, would eventually lose its oceans as solar radiation intensified, leaving behind a parched desert world. Mars, though colder and farther, might warm slightly under the expanded solar output, altering its carbon dioxide cycle, though not enough to restore ancient rivers or seas. The giant planets, their atmospheres less affected by solar heating, would maintain familiar appearances for longer, though their moons might undergo subtle transitions as ice sublimed or migrated. Beyond the solar system's lifespan, the planets faced more distant fates tied to the Sun's eventual transformation into a red giant. Mercury and Venus would be engulfed. Earth, depending on tidal effects and solar mass loss, might barely escape consumption, but be stripped of its atmosphere. The growing discipline of exoplanet research fed back into this understanding. Thousands of discovered exoplanets formed a cosmic laboratory of planetary diversity. Worlds larger than Earth, but smaller than Neptune, super-Earths and mini-Neptunes were common elsewhere, but absent in our own system, prompting questions about why the solar system lacked these intermediate types. Hot Jupiters orbiting their stars in days revealed how migration could produce extreme configurations. Rocky planets skimming the surfaces of their stars exhibited molten oceans of lava, contrasting sharply with the temperate environments once imagined for terrestrial worlds. Water worlds, carbon planets, and tidally locked bodies orbiting red dwarfs expanded the planetary taxonomy beyond traditional categories. This kaleidoscope of planetary forms forced scientists to reinterpret the solar system not as the template for all systems, but as one outcome among many, shaped by specific initial conditions and evolutionary pathways. By comparing these distant worlds with Mercury, Venus, Earth, and Mars, planetary scientists refined their criteria for habitability. They learned that magnetic fields could protect atmospheres, but were not guaranteed, that oceans could form from outgassing or external delivery by comets, that atmospheres could be stripped by stellar winds or replenished by volcanic activity, that tidal heating could foster habitable conditions even far from starlight. These insights fed back into the understanding of our solar system, illuminating how fragile the balance of habitability truly was. Through all these developments, the planets remained both historic and contemporary subjects of fascination. Their ancient surfaces preserved evidence of epochs long past, while their modern-day phenomena reminded scientists that planetary evolution never ceases. Dust devils whirled across Mars as it retained traces of ancient rivers. Volcanic plumes burst from Io, while its mountains shifted under relentless tidal stress. Neptune's storms erupted and dissipated unpredictably, hinting at atmospheric dynamics not yet fully understood. The rings of Saturn, composed of material perhaps only tens of millions of years old, orbited a planet more than 4 billion years in age, juxtaposing youth and antiquity in striking contrast. In this interplay of past and present, observation and theory, exploration and imagination, the story of the planets grew ever deeper, its threads weaving through human history, scientific progress, and cosmic evolution alike.